Hi guys, this is Dr. Anna and we are continue with segment 5 of the historical geology sequence. We are on the first module. It's called the Geologic Time. So let's jump in. We have to continue with the types of decay. And the first kind of decay is the alpha decay. If you want to see the symbol of the alpha decay, the way we write it is the Greek alpha, which looks like that, and we usually say decay. So if you look at the scientific book, this is how they will show you. So what is the alpha decay? You have a parent nucleus. In this case, it's the uranium-238, and that's how I say it because that shows you the mass number. So we could really actually calculate the number of neutrons by 238 minus 92, which is the number of protons. But let's not do that now. So when the decay event happens, helium nuclei is going to emit from the unstable nucleus, which is the parent nucleus, and then the daughter will form also. Okay, so what happens? The helium nuclei has the mass number is 4 and the atomic number is 2. So when the daughter nucleus forms, that it will have 4 less mass number and 2 less number of protons. Okay, so 238 minus 4 is going to be 234, and 92 minus 2 is going to be 90. So it's easy. Actually, I will show you the nuclear equation in a minute. If you add back the 234 plus 4, you're going to get the 238. And if you add back the 2, 90 plus 2 is going to give you the 92. So you can see that this is kind of an easy way to see what happens, what is going to be the daughter nucleus, okay? Now, this decay is a so-called ionizing radiation, and the reason for that is because the alpha particle only have 2 proton and 2 neutron, but it doesn't have electron. So therefore, it will have 2 positive charges. The symbol for this is the right here. So it's a Ag because it's a helium nucleus and it has the mass number as 4 and the number of protons or the atomic number is as 2. Okay, so I hope you understand that. If not, then just let me know somehow and I will explain it, try to explain it better. But now I'm going to show you the nuclear equation. So here is uranium 238, which is, remember, the mass number, and 92 is the atomic number, which is equal with the number of protons. When you have the decay event, the helium nuclei is coming out of the parent nucleus. And if we do the 238 minus 4, it's going to be 234. That's going to be the new mass number. And 92 minus 2 is going to be 90. And you're just going to look up what is the atomic number of 90, what element is that, and you will see that it's a thorium. So it's really simple. Now, I have an equation here when we have to solve it. In this equation, we're going to use radium, Ra, which remember Madame Curie discovered. The mass number is 226 and the atomic number is 88. Remember, that is the number of protons. And it is decaying with the alpha decay. Remember, the alpha decay is the helium nucleus. When the mass number is 4, the number of protons are 2 or the atomic number is 2. So what is the new element? What is what forms here? So the way we get it, remember that 226 minus 4 will give us the new mass number, and the 88 minus the 2 will give us the new atomic number. So 226 minus 4 is going to be 222. And the 88 minus 2 is going to give us the 86. And 86 is the radon. So it's Rn. The new element is going to be 222, 86, Rn, which is the radon. That's what you got in your houses if you live close to mountains which have granite with some radium or uranium there. Okay, so this is our solution for this element, for this nuclear equation. Okay, the next type of decay is the beta decay. Now, the Greek beta looks like this. Okay, so the scientific journals, they will say beta decay. I just spelled it out here because I cannot write with the computer the beta. So that's the Greek beta here. So beta decay is a process where an unstable atom becomes more stable by giving off a small particle called beta particle. Most of the time, this happens by a neutron in the nucleus emitting an electron and becoming a proton. So therefore, the atomic number is going to go up one, but the mass number is not going to change at all. So this is the symbol of the beta particle. Okay, so it's an electron, but the mass number is equal 0 and it has one negative charge. Okay, that it is. And here is the nucleus and the beta particle, which is a fast moving electron basically. And that's why that neutron becomes a proton, because now it loses the neutrality because the electron goes out of it. Okay, so it becomes a proton. Atomic number goes up by one, mass number is going to stay the same. So let's see an example here. So the carbon 14, which we all have heard about, I already talked to you about. Carbon 14, so the mass number is 14. The atomic number, which is the number of protons, is 6. And it will decay by a beta decay. If we write down the beta particle, and then it will have this negative 1, then the way we can get the 6 back is that we go up by 1 on the atomic number, which is the number of protons. So instead of 6, we're going to write 7 and the mass number is going to be the same. So this is how we check if we did well. Here, 7 minus 1 is going to give us the 6. So we did good. And we didn't change the mass number 14 and 14. So it's that simple. Okay, now we have another one which we have to solve without writing it down. So here is the bromium, 82. The 35 is the atomic number, which is the number of protons, remember? And it will decay by a beta particle. Tell me, what's going to be the atomic number of the new element? Remember, it goes up by 1, so it's going to be 36. What will be the mass number? Remember, there is a 0 here. That just means that it's going to be the same. So it's going to be 82. Now we just have to look up what is the 36. Okay, it's a krypton, Kr. So you see, I don't know all of it. So it's going to be Kr. 82 as a mass number. 36 is the atomic number. And it's Kr, the krypton. It's a noble gas. Okay, the third kind of decay is the gamma decay. The gamma is the Greek gamma. Now, when you have the gamma decay, basically it's just gamma rays. And this is a type of electromagnetic radiation which results from the redistribution of electric charge within the nucleus. A gamma ray is a high energy photon, basically. For a complex nuclei, there are many different possible ways in which the neutrons and protons can be arranged within the nucleus. So gamma rays can be emitted when a nucleus undergoes a transition from one such configuration to another. For example, this can occur when the shape of the nucleus undergoes change. Neither the mass number nor the atomic number is changed when a nucleus emits a gamma ray. So gamma ray usually doesn't come with the nuclear equations because nothing is changing. This is all you can do. So you're going to write down one kind of configuration and you can see that it's going to be just a little bit different inside, and a photon, which is the gamma particle, comes out of it. So you don't have to know any more about this. Okay, so here is an exercise we should do. Polonium is the scarce natural element. Remember, this is the element which Madame Curie discovered. Radium and polonium. She named polonium after her original country, Poland. It's a very rare natural element. And we have to write an equation for the alpha decay of polonium 210. So it's PO 210 is the mass number. And to tell what isotope is forming by the reaction. So it goes by a helium 4 and 2 plus, we have to figure out, like we have to look up the polonium. So atomic number of polonium is 84. So the question is, what are the new numbers going to be? Remember, we had the helium nucleus is coming out. So what happens with the mass number? Yeah, it goes down by 4. So 210 minus 4 is 206. And what happens with the atomic number? 84. It's going to be 82. I hope you're saying the same thing. And now we just have to figure out what is the element with the atomic number. It's the lead. So it's going to be the lead 206. And the atomic number is 82. So I hope you come up with the same thing when you were doing it with me. I think you did because we went together. So let's see if we did the calculation right. 206 plus 4 is equal to 10, so that's good. 82 plus 2 is going to be 84. So you can see that the nuclear equation is about the easiest chemical equation you can actually, or you want to learn because it's easy. So this one is a cobalt radioactive isotope, so it's CO, which used to treat cancer, identified the nuclide in the reaction in which cobalt 60 undergoes a beta decay. So we're going to have to write down the beta particle, which is the electron minus 1 and 0. And then we have to figure out, first we have to know what is the atomic number of cobalt, 27. So the atomic number is 27. So it's 27. What is the element which forms here? Remember what happens with the mass number? Is it going to change? There is a 0 here. So the mass number is going to stay 60. And what is going to be the atomic number? It goes up by 1. So it's going to be 28. It is actually the nickel. If you have a cobalt isotope, which is 60, cobalt 60, and it decays by a beta decay, it's going to become a nickel, which is 60 mass number and 28 the atomic number, which is the number of protons, remember? So we just did it. This is simple. And we can check if we did good. 28 minus 1 is going to be 27. 60 minus 0 is going to stay 60. So we did good. We are good. Okay. So now we are talking about radioactive isotopes. Every element will have at least one radioactive isotopes. And for example, the hydrogen. The hydrogen have a radioactive isotope, which is tritium. We call it tritium. And the tritium has one proton because it's hydrogen, obviously. So the tritium is one proton. And because the mass number is 3, it has 2 neutrons. Okay, so that's the tritium. And we use the tritium a lot for determining the age of groundwater movement. So it's very good and very useful element. But some of the heavier elements, such as platinum, have as many as 30 radioactive isotopes. It's crazy. 1,200. About 1,200 different radioactive isotopes have been produced by nuclear bombardment in nuclear reactors or particle accelerators, artificially producing a lot of radioactive isotope. And it's important because we use it in nuclear treatments. The further the neutron to proton ratio varies from that of the stable isotopes, the shorter is their lifetime. Artificially produced radioactive isotopes have a half-life in the range from fraction of a second to some years. Question is, how do we use these radioactive isotopes? We have about 200 different radioisotopes, which are currently used in a variety of applications, such as in food and agriculture, industry, or even medicine. You probably know that. So, how do we use them in food and agriculture? The radiation emitted by radioisotopes is used in different ways, like insect eradication, food preservation. You probably have heard about that. Like, you know that we can get rid of bugs by it. We can do fertilizer labeling. We can genetically alter things, or we can do sterilization. How do we use it in medicine? Radioisotopes are key in modern nuclear medicine. There are some really important uses like sterilization, medical diagnostics, and medical treatment. Like somebody has cancer and they have to do radiation. They figure out what kind of element is the best for that kind of radiation, and then they will do it accordingly. Usually, if it's an alpha decay, They don't really use that because it's very destroying. The most of the time in radioactive treatment, they use beta emitters, which means elements which do beta decay, and that just goes 1 inch into the human body, so they can really concentrate the radiation rays into the cancerous cells, and they can really treat cancer with that. These are some of the isotopes which they use in medicine. You can see like bismuth 213. Of course, I just collected data on this. I don't really know much about nuclear medicine. Nuclear medicine is the name. And if you ever have to go there, you cannot be late because they make radioisotope for you. And if you are late, then it starts decaying, so you don't get the treatment you're supposed to get. There is the cobalt 60, iodine 125. They used it to me. No, that's not what they used for me. They used iodine 137 to kill my thyroid because I had Graves' disease myself. There is a lot of things. If you're interested in, then you will be able to read it right here. What is really interesting that during my research, I figured out where in the world are making nuclear medication, like isotopes for nuclear medicine. And what I figured out that none of the nuclear reactors are making nuclear medicine for the people in US. We have to bring them from other countries. Most of the time we get our medication from Canada, see South Africa, Europe, and Canada. So North America gets 60% from Canada, and of course some from Europe. But isn't that interesting that not one nuclear reactor is making medication for American people? It just went think I'm going to just stop right here and finish this segment because we don't have that many slides left. So I can finish it in the next segment. Okay. So I'll see you there.